Hey there, party people. Wow, topic 4.4, our last topic before, break ever. So, except for some review videos, maybe, this might be your last ever flipped lecture. Just take it in. Yay. Okay, topic 4.4. We've been looking at carbon building up, different ways the carbon cycle has been disrupted, right? So taking out of those reservoirs and not putting back in. So now we're going to look at, so why does that matter? What is carbon doing to our Earth and the implications of of human activity. All right, so we're going to be focusing on climate change. Okay, hopefully you have some, I don't know, say, oh look, that's a very image straight from the IB test there. Some knowledge of greenhouse gases and practices, and the ocean acidification might be new to you. We'll talk about coral reefs, and then in class we'll be looking at the different claims. So there's 4 different claims for climate change, and looking at the precautionary principle. So let's get going. Okay. All right. So first of all, let's classify greenhouse gases. So greenhouse gases are naturally occurring, right? So we'll talk about the importance of greenhouse gases on our Earth. But for the most part, the greenhouse gases in our atmosphere, the majority are water vapor, right? Looking at clouds, things that trap heat in. And what classifies a greenhouse gas is something that absorbs the long wave, infrared. Absorbs and emits the long wave infrared. So it traps heat, right? So basically, remember we talked about the types of light. Light can come in as visible light, and then as it loses its wavelength, that becomes heat, right? Infrared. Again, natural phenomenon. It's only about 1% of the atmosphere, so a very small percent, but those slight percent changes can have big effects, right? The two most that we are concerned about are carbon dioxide and water. Methane and nitrous gas have a far less of an impact, but still things that you need to know. Okay, so again, carbon dioxide about 4%, 3.5% of our atmosphere, water vapor 95%, but a very fine balance, right? It's important to keep these things in check. Okay, so of those greenhouse gases, right? Anthropogenic gases. So anthropogenic is looking at man-made gases. So man-made, greenhouse gases. So men, not women, right? Carbon dioxide, right? So we get carbon dioxide added by combustion, which is part of the last part of your carbon cycle. So when we burn fossil fuels, we get combustion, and carbon dioxide is released into our atmosphere. We get methane we talked about that beautiful smell from cattle, right? Also from landfills. You can usually smell those too. Like if you live anywhere out like West Park, right, where the dump is, we get methane gas, and we also get nitrogen oxides, right? And these are emitted for vehicle exhaust. We've got a lot more regulations lately on bringing those back. A lot of reform on, passing a smog test. That used to not exist, right? So now you have to have your car pass that test so that we know that those gases coming out are fit within the range that they should, right? So this human activity, these greenhouse gases, is changing. It's changing the proportions, right? So of the man-made greenhouse gases, right, they're anthropogenic, 84% of them are carbon dioxide, 9% methane, right, that 5% oxide, and then the fluorinated gases. If you want to just sketch these out or leave some room in your margin across from it, I'll let you guys add the diagrams during class if you don't want to add that right now, but it's important to know those numbers and we'll have that visual. Okay, so what does it matter? So what does the greenhouse gas do? You probably felt the impacts of the greenhouse effect, what we call, if you've let your car sit in the heat, right, all day. Like it might be 80 degrees outside and then you get in your car and it's 95, right? And that's because the light that goes in through your windows loses some of that wavelength, right, gets longer, and then it's trapped as heat, so it doesn't go back out. Right? And so that greenhouse effect is happening here on Earth, and we are trying to figure out how much of that is, long story short, how much is human impact and how much is natural. Okay, so the impact. So 2 factors are going to determine, its impact on our atmosphere. So first of all, its ability to absorb long-wave radiation. So gases with a greater capacity to absorb it have more of a warming impact. And then the concentration. So if I increase the concentration of the gas, the temperature is going to go up too, right? And the concentration is determined by how much it's released and then its persistence. So its ability to persist in the atmosphere versus be taken back out. Okay, here's an impact summary. Again, why don't you just leave some space across and I'll have you guys copy this down. But we are looking at, so the 4 different, up here, these are 4 different greenhouse gases. And we're looking at these different categories. How much is in our atmosphere, how much it's been increasing, how long it stays, and then its potential, right? And so these things are classified as very high, low, normal, very low, short, or non-applicable, right? So we do not have any data for that, right? So our atmospheric concentration of water is very high right now, but its lifetime is very short, which means water goes in and out of our atmosphere relatively easy, right? So evaporates, clouds, comes down as rain. So it comes out of there very quickly, 1 to 5 days. However, carbon dioxide should have a low concentration. We're seeing it increase, right, at parts per million per year. This is parts per million, parts per billion. And concentration stays in the atmosphere a long time. So it's not going in and out like our water does, right? So 5 to 200 years. And I'll show you how we can look at carbon dioxide over time as well. Okay, so we'll put that in class. Okay, so this is what I just explained earlier, right? And if you like draw a car in your notes or something. So natural process is actually really important. The greenhouse effect is why life is possible on Earth, because it regulates the temperature. We get the clouds that come in, it traps that heat. And so we do not see these huge fluctuations like we do on the moon or on Mars, right? And so the greenhouse effect, very, very important for maintaining life on Earth. However, it is, again, something that needs to be regulated. Okay, so you can read through these. This is everything I just explained back in the car example. But right, that UV invisible coming in, it's re-emitted as a longer, which is heat, and trapping the heat prevents those temperatures from going up and down, which allows life to exist. Okay, here's a visual of that. Right, so no greenhouse gases if I have the sun's radiation coming in and it's just reflected back out. But here with the greenhouse effect, I get some of that heat trapped back in, and again regulates those temperatures on Earth for life. Okay. However, the industrial practices, I'm going to let this go without the sound so you can kind of look at that too. But this is looking at a year of carbon dioxide over a year, looking at the concentrations. But what we're seeing from humans is that we're increasing those concentrations way too fast, right? A couple different ways. We are destroying the things that take carbon dioxide out, so deforestation, right? So getting rid of all photosynthetic trees. I get less carbon dioxide coming out. We are increasing agriculture for food, so we get increased productions of methane. But the primary increase in carbon dioxide is the fossil fuels. So coal, oil, and gas that we are burning for energy are going into the atmosphere way too quickly. And we're seeing these huge amounts. You can see like over time, this red, not good. You can see how carbon dioxide moves though too. It's a gas, so it's not like it's stationary. You can see the areas, right? Northern California, Europe, India, Asia, right here, China, huge impact. But we're seeing it go across, right? So just because we have certain areas creating it, it affects the entire world, which is why things like the global climate Senate, people that come together are trying to regulate all countries, not just some of them, because it has the global effect. Right? What we've seen then over time is, so carbon dioxide is down, we've seen our climate change. So we've seen a clear correlation, again, correlation, not causation, is that as carbon dioxide goes up, we see global temperatures go up. This, again, is not anything new. We'll look at some data over time. We're able to look at years and years of carbon dioxide data in Antarctica, because when ice forms, so it's from the ice cores, when ice forms, it actually traps gas inside, and so we can look at the concentration of carbon dioxide at that time. So they do what's called an ice core, kind of like the core of a tree, like they just drill down, they take it out, and you can actually see over the years the carbon dioxide level. We've been able to do this over the past 355,000 years. And so what we have seen over time is anytime we've seen natural ice ages and warming ages, we see the carbon dioxide levels increase or flux with it. Okay, so we see that when our carbon dioxide levels go up, we've seen atmospheric temperature and go up as well. All right, so this is the next graph. Again, we'll kind of sketch this in class, but I want you to look. So the red is temperature, right? So this is at 300. So looking at every 100,000 years, we're looking at the temperatures here, right? So you can see that there's definitely a correlation, right? That is what concentration of, carbon dioxide is done and temperature is done. And what we are seeing now, though, and I'll show you in a second, is this natural kind of increase. Oh, sorry, I was going to say, because carbon dioxide is also emitted, we talked about like natural things like volcanic eruptions. So we've seen things like huge volcanic eruptions release all this carbon dioxide, and we've seen a global climate change, right? So naturally going in and out, in and out. However, the concentration of CO2 right now is here, right? So we've seen the natural concentration kind of go up and down, up and down. We're looking at seasonal changes too, kind of go up and down. But right now we are way up here in parts per million, so far past anything that's happened historically. All right, here's some more recent data. Again, I'll talk about for a second, but we are going to be putting it into our notes in class, right? So temperatures variation over the centuries. This is just from the last 150. Oh gosh, almost past 2020 now, right? 270, almost 200 years ago, looking at temperatures and then carbon dioxide, right? So again, pretty clear correlation between the two. All right, so the consequences of that, so why that matters. So scientists predict that with our greenhouse emissions staying as they are, we see not only the global temperatures increase, but we see really extreme weather. I'll show you some examples of like Hurricane Katrina, but anytime we get really, really warm water and those hurricanes or storms come across, that fuels those storms. So we get tons of evaporation happening going into those hurricanes. So as they approach warm waters, they go from being like a 1 or 2 to being like a 3, 4, 5. So catastrophic storms that we haven't seen in places before. So not necessarily, all the time, but we see heat waves, cyclones, tropical storms, things that are uncharacteristic. And we based if you've done any studies on human population and geography, where people live is based off of the resources, right? People have built towns and cities and countries and places because of certain reasons, being able to stay alive during temperatures because of flooding. And so we're seeing all these different fluctuations that are having huge impacts across the world. And then more importantly, or bigger one kind of globally, is the circulating ocean currents. So longer, warmer years, longer, cooler years, things that the belt that's meant to distribute heat, especially like in the Atlantic, when that stops, that's when we see things like ice ages occur. Okay. Another, like I said, this one might be, so climate change might not be new to you, but ocean acidification might be something that you are new to. We talked about in the last lecture, these carbonic acids. So carbon dioxide of the ocean is actually a major sink, that takes the carbon dioxide out of the air. So it's a good thing. However, remember when we blew our carbon dioxide into the water with the indicator, it turned from that blue to the yellow pretty quickly because carbon dioxide fixes and it makes it slightly acidic. So we're changing the pH of our oceans, which is not good for life in the oceans, okay? And so we've seen the pH drop a 0.2, which is a huge, especially in places that don't see a lot of change, that's a huge impact, all right? So again, looking at the carbon dioxide levels and the pH, we see a negative correlation. As one goes up, the other goes down. So the places we see this the most are in coral, places that have coral reefs. If you know anything about coral, the outside has this symbiotic algae that goes on the outside. It gives it its color, and it's what creates just life in the coral reefs. The coral reefs have a really consistent temperature all year. Like if you look at the places we see coral reefs, not a lot of fluctuations. So we're not seeing a lot of biodiversity as far as surviving. And so as these acidic or acid levels go up, that's needed for this shell and the exoskeleton development, they cause this mutualistic algae doesn't live there anymore. And so this is a very simplified version here. But did I open it? I did. Here it is, because I was looking at before and after. So if you look at things like before and after, and usually it goes before, after, and then dies. Yeah, like this. So what it looks like healthy as it's dying and as it goes. And as you see the life and the color go away, you see also the impacts on the ecosystems around it, right? So definitely kind of a sliding effect. Okay. All right. There are 4 claims for climate change that we will look at in class. So, so again, if we're not saying that it cause or cause equals or correlation equals cause, sorry, there's different claims as to why and how like the carbon dioxide is increasing. So you do need to know these 4 changes: the natural solar activity, that it was increasing before emissions. However, we're going to look at those in class, so don't worry about those for now. All right, so the last thing we are going to look at is what we call the precautionary principle. So it's actually not just, I'm going to say for science, but it applies to this situation, right? So when human activity raises a significant threat of harm to the population, measures should be taken in the absence of scientific consensus, right? So the precautionary thing says that if this is going to happen, there's a significant threat, even if we don't have all the scientists completely on board, which like 99% of scientists are, we should take action, right? We should not leave that to chance, right? And what those 2 things are called is actually psychological principle. So the burden of proof, right? That prove will be boiled alive. Like, so there's people that say like, you need to be able to prove it. Like, if you cannot prove it, then we should not, take all these changes, like cut emissions, cut back on fossil fuels, things like that. The precautionary principle says if the only way to prove it is when it happens. So if you prove it, then this is too late. It's too late, basically. The only way to prove that something will happen, especially with climate change, is for it to change, and then we cannot reverse it. Right? So this is called the precautionary principle. Even the lack of complete consensus, if we have the majority, like 99% of scientists, then there should be something done about it. Okay, and that, my friends, is the end of 4.4. Here are those review questions. We will look at those in class. We'll add all of those diagrams and look at the 4 different debates. But bring this to class. Be ready to add those diagrams, and this is it. I feel like now that I've said that, knock on wood, you'll have something else. All right, have a fabulous day.